We're going to start off talking about aquifers. You have these notes available to you. In there, I have a number of figures and calculations that you can fill in as you go along. I've also pasted in there some figures from our text and from a couple other sources. So groundwater is water in the ground. It's part of the overall hydrologic cycle. So the groundwater we're dealing with came from the surface at some point, and it went infiltrated down there, and it's going through these aquifers. As I'll explain in a second, aquifer is a formation in the ground that we can get water out of, and then it can go into lakes and streams and springs and come out of the ground on its own, or with us putting a well in there and getting it out of there. Now, there is an exception to that. There's something called connate water that when the geology, the rocks were laid down, whenever there might have been some water in there initially. But in general, the water we're dealing with has not been in there forever. It's part of the overall hydrologic cycle. So we divide aquifers into two general categories, an unconfined aquifer and a confined aquifer. So if I dig a hole in the ground, a well is a hole in the ground, and I dig down, at some point there, I might hit some water. So I'm going to draw the water level right there. So that's the water level. And I might go down here somewhere and dig a hole, and I might hit the water there. So that's the water level in the well, and we're going to assume that's the water level in the ground. I'll talk more about that in a little bit. So we'll have, I can kind of assume it's straight along there, slopes like that, and that is the water table. Now, if it's sloping down that way, I have a gradient in this direction, so it changes head. Later on in these notes, we'll do a little exercise on the head, and there's a distance in between them, and the slope indicates the direction of the water. So water flows downhill. That's true for groundwater as well as surface water. So if it's going from up here to down there, that means I have flow in this direction. Now, a couple other terminology here. Of our unconfined aquifer, it has a water table. At the bottom of it somewhere, it has a confining layer. So in the ground, confining layer. That's impermeable, rock or clay. In the ground, things tend to be laid down in layers. So there's probably a layer of rock or clay down there somewhere, and the water is on top of it. This is an aquifer because it gets water out of it. We might call this, I don't know how often I've heard this term, an aquiclude, but generally we just say confining layer or impermeable layer. Down here, it's the saturated zone. So it's all full of water. I'm going to scroll down lower in the page here in a little bit, but it's the saturated zone. As opposed to above the water table, it might have water in it, but it's I put my water level too high here, the unsaturated zone. Oh, I can write that in there. That's above the water table. By the way, it could be that we go down and we hit some water here somewhere, and we think, yay, we've hit the water table, but start pumping it out, and it's gone pretty quick. And it turns out we might have, it's just up there on a little, again, there's a little layers in the ground. So that might be a perched aquifer. So again, our aquifer here, we have our two wells here. Each well has a specific head that we measure, and that's above the confining layer. For an unconfined aquifer, it doesn't matter what the datum is. For a confined aquifer, it does matter what the datum is. So the change in head, that's an equal sign, would be H2 minus H1. And then the gradient, I'm getting ahead of things a little bit, would be over the distance between them. Another note, the unsaturated zone, sometimes they call the vadose zone. I don't know why. So in the vadose zone or unsaturated zone, you might have some water, but it's not filled with water. So we'll talk about the degree of saturation. If it's 100% saturated, that means all the pore space is filled with water. 0%, there's no water in there. So it varies in between there. And as you get close to the water table, it gets higher. You actually have a capillary fringe right above the water table. So in the spaces inside the soil, the sand, they're really small, so they act like a little capillary tube, real small, and the water will rise a little in there. So when you dig down, you might actually hit water, might be super wet, like 100% wet right there, but then it's not. If you put your well in there, the water level won't be there. The water level will be where it's completely saturated there. So it'll rise a little bit above the water table there. And one of the reasons I mention that is that I'll talk a lot in this course about we'll do a section, the last third of the class, on transport and fate of contaminants. And I work now in remediation and did for years. You can have, if you have like some gasoline on there, it'll kind of float on top of the capillary fringe. Now, this will move up and down over time, so it'll get smeared there, but it can actually then drop into your well here. And you might think you have a lot of gasoline there, but actually you have only a little layer there, and it's just coming into the well like that. Now, this is a little unrealistic because we actually have the well here this is the screened interval. This is the water comes in. So if this is done right, the water can't actually get in there. And actually, I'm going to take a little aside here just for a second. This is a lecture or two ahead, but I pasted in here a diagram of a well, what it looks like. So what I was saying is that you have a screen interval. So a well is a hole in the ground. You put a pipe down in it, and then you seal it real good so it only lets in water where you want it to come in. Where you want it to come in, you put a screen in there. That's the screened interval. So this well, water would only come in here, and then the rest of it would seal it from coming from outside. I might, for monitoring at a remediation site, I might have a well where I purposely have it screened on the water table so that it'll let water in there and I can know right where the water table is. And that's the case I was talking about, where we could have the gasoline leak in right into the well there, the gasoline that was floating on top of the capillary fringe. So back to our aquifers, this is an unconfined aquifer or a water table aquifer. Now let's talk about a confined aquifer. A confined aquifer is where the water is squeezed between two different confining layers. Now, this can happen down here, that the water is infiltrating into the ground here. Again, it's coming from the surface somewhere. And then you have these layers of clay or rock that are impermeable, and the water is in there, and rain keeps coming down there, so it comes under pressure. If I have a confined aquifer is by definition under pressure. And if I dig a hole down in there, and then I get down here between these layers and I put a screen in there, the water, because it's under pressure, it will rise up, and I'll put it maybe about here. So that tells me the head or the pressure where the screened interval is. It tells me nothing about what's outside right here. It only tells me the head right there. And so I'll do again where I dig another hole down here. I also screen that one in between those two layers there, and I have a point there. And now if I look at the difference between those, I'm actually going to draw a dashed line here. And I'll explain why in a second. Kind of missed right there. But this slope is the slope of it's not the water table exactly, the change in head. We might call it the phreatic surface or the potentiometric surface. Potentiometric surface. It's not really where the water is. It's where the head is, or where the potential is. And so you have two confining layers here, an upper one and a lower one. Oops. Well, what happens if we get this drawn down below that? Then we just have an unconfined aquifer that's down below some layers down there. But a confined aquifer is under pressure. So we have a confining layer. This is, again, impermeable. Well, I said clay and rock. Is it either or? Either lets a lot of water through it or nothing? No. There's different permeability, and there's some that are like almost impermeable. And we actually have methods for when we do aquifer tests. We'll do some simple aquifer tests in here. We won't get into a lot of the details. And we might actually have a leaky, use the highly technical term, leaky aquifer. So it's not quite zero, but it'll come in. So some other terms we have in here. We have the aquifer thickness, a number we'll need. We'll use a B for that. I'll double check and make sure the text uses a B, but that's pretty standard. So that's the aquifer thickness. It's a number we'll need. By the way, anybody know what it's called if we have so much pressure that we get water out of above the water surface? We call that an artesian aquifer. Now, we're a lot of people use artesian to mean any confined aquifer, which I guess is okay. But kind of rigorously speaking, artesian aquifer is one that comes out by gravity. So you could see how that could happen if you had the ground surface sloped. And I hate to make too many lines in here, but if the ground surface sloped like that, it'd be above the surface. By the way, if the ground surface sloped like that, what do you have? You have water. So you can have water coming out here, and that would be a spring or a seep. So an unconfined aquifer can lead to a spring, but a confined aquifer could also lead to a spring or a seep with the water coming out. So that's a quick introduction to aquifers. Next, we're going to move on into Darcy's law and then aquifer properties, do a little slightly different order than the text, but that'll be the next video.